Yes, I'm very pleased and honored to take part to this event after 10 years of research in the domain of grid impedance measurements, especially with the high qualified expert you have in the event. I think my first power quality book was actually written by Professor Detlef Schulz. So
okay.
Nervous
so
about
great.
this.
And yeah, maybe I would also lose some sentence to you. Yeah, as I have said, you are associate professor now at the Applied Science University Valais-Wallis in Sitten, Switzerland. And yeah, you are you teaching and researching in the field of industry, electronic, and smart grid. And I know you from the project ZNet, where you are working on standardization for grid measurement, how we can yeah, compare the measurement results from different measurement devices. And it's very interesting. And we have used your impedance test equipment. And that's the reason why you are here. And yeah, I'm very proud and yeah, the stage is yours.
Okay, thank you. Yes, we have a research activity in the domain of integration of renewable to the grid. We are a small university and a small team, but we are really happy to have access to very advanced tools and a very nice GridLab with energy in feed on different forms, and also a low voltage DC network, for instance. But we come from the power electronics. That's maybe the main aspect or the angle of view from which we look at the project. So converters. This presentation is more about standardization of frequency and time-dependent grid dependence measurement in the frequency range of power line communications. And that's the ZNet project itself. The main outcome of the project has been to develop samples of static grid impedance that can be used by other partners, either to evaluate their analyzers, like we have seen a couple of examples now, and maybe to go towards some standardization of the definition of the grid impedance measurements or definitions itself, and how do we proceed to measure it for standards, for instance, to have a better tools than just the VAMN that it was mentioned before for the measurement of impact of different interferences on power line communication, for instance, and so on. We have been able to make comparative tests, and we will continue these comparative tests with the programmable grid impedance. Okay. Okay. Looking at different aspects on the grid, we had already discussed about that. We have the components which will affect the impedance on the local point. And then when we connect several equipment, then we have variation of the resonance points, resonance frequency and magnitudes in time, in the frequency range too. But when we look at the grid, we have quite different picture. We have to maybe use the statistics to have a more coherent picture of all what can happen. So it's very wide spectrum of measurements that we need. What we can do with measurement of impedance, you can see the example of the analysis of the connecting point of EV chargers, several models of EV chargers and PV converters. And what we can see is that there are some resonance at some frequency, depending on the components on the loads and the grid itself. And if we try to identify those components so that we can create a circuit model, and from this circuit model, we can then make assessment on the grid or make prediction of how the impact will be on different communicating systems, for instance, on stability of converters, according to presentation of Professor Lieser, for instance. So to create this model, we have possibility to measure online the impedance and then to make our simulations. The project to establish metrological traceable grid impedance standard is supported by Swiss Federal Office of Energy, and the objective, beside making the samples, is also to try to agree upon measuring methods. At least to make a catalog of methods and to compare them would be already a very big step to achieve. We are lucky to have partners from industry and universities, not only in Switzerland. TU Dresden is a very important partner, as well as University of Basque Country, the HES-SO group. So we have on one hand the team of Jan Meyer, and on the other hand the team of Professor de la Vega, who have shown a lot of interest for this project. So I already mentioned the objectives: to design characterized static and programmable and variable grid impedances, to compare them, and then to work on the establishment of common method for the standardization. So looking at the power line communication, you know that the frequency range to feed signals with very advanced modulation process, the band between 35 kilohertz and 92 kilohertz is actually used from the Selenek A band, and there is a trend towards moving higher frequency in the FCC band. Now, the power line communication is coming in competition with noise generated by converters. They are in the same frequency range. That's one issue. And there's been a lot of effort to create standards, to develop standards to tackle down the emission of converters. But if we look at the communication process and at the communication channel, we can see that the impedance at the connecting point is also playing with the transfer function for the whole communication. So if we have in parallel to the in-feed or the injection point of the signals from, for instance, from a smart meter, and we will look the signals at the end of the line, we have an attenuation of the signals, of course, due to the transfer function of the line, but also to the access impedance. And here you have typical case of a battery charger with low impedance in the 60-70 frequency area, and you can see that there is a strong attenuation of the signals that match to this input impedance. In the project, we have started to make investigations in a laboratory, not only on the site, because we want to really know what we are measuring, what kind of interferences, what kind of impedances. So we have made quite truthfully tests together with UPV in Bilbao at Tecnalia, where we have 40 smart meters and different loads. And we have also had the chance to be able to use an impedance stabilizer developed by Schaffner. So we can see how we can change the communication when we change the impedance on purpose. Here are the measurements realized with the device developed by TSR in UPV. And you can see that without the stabilizer, we have very low impedance for the devices connected to the connecting point below 100 kilohertz, and a strong variation, some variation in time. You can see that when we include the stabilizer between the loads and the connecting point of smart meters, we lift up all the impedance in the communication frequency area. You can see there is still a dependence in time, of course, but it's already better in all the cases. So we have conducted many measurements. I don't come too much in detail here. It's just to present one case that when we had together those nonlinear loads, LED lights, with a behavior that is corresponding to the colleague Miller has presented just before, if we had a strong noise at the time, we lose the communication systematically. But when we add this impedance stabilizer, we lift up the access impedance, actively, we can see that the communication is coming back within a few minutes. So this shows the impact of this line impedance only. The noises have not changed, the loads have not changed, it's just artificial liftoff of the access impedance. All right, about standardization, the first device we created and made available is together with METAS, Metrology Institute of Switzerland. It was the idea to create an impedance that it's matching better to the grid statistics than the AMN defined by CISP for the tests, for instance. So we can see that the grid impedance is much lower normally, and it has also not so many resonance. So we have added some resonance in order to challenge a bit the devices. To realize that, we took actually the VA-AMN defined by CISP, market available products, and we have added some impedances in parallel, capacitance, inductance, and resistors. And we put that all together nicely, and we get this profile. So the profile is lower in magnitude usually, and we have one serial and one parallel resonance, so we can change a bit affect the measuring process in terms of resonance. A very important aspect when we compare those measuring devices is the impact of the grid that is feeding the impedance. You can see that in the frequency range for PLC, we have quite stable situation, but in lower frequency, we can have very big difference, very large difference if we have a grid simulator, because this is an active system and it will affect the impedance by the converter itself. In the very high frequency, we have the noise, and this is probably common mode noise because it's very, very high frequency. So we start to have disturbances also in the higher range. But in our range, things are going pretty fine. In order to increase the flexibility, we have decided to develop a programmable impedance, so we can change different parameters. We can change the components. It means the frequency, resonance, and the magnitude. And this has been packed and developed very nicely with programmability by METAS. And here you can see the results about 60 different impedance combinations that are available. And you can see a variation between, on the whole spectrum, between 0.5 ohm to maybe 50 ohm. So this device is now available, and it has been slightly modified with a net synchronization so that we can switch from one behavior to the other very fast and synchronize with the grid. So it means we can have now a varying behavior of the impedance, which is programmed and controlled. So this will help us to characterize impedance meter and also the impact of this special impedance on the communication systems. For the comparison, we have run the comparison now between different entities that are partnering to the project. The 4 available impedance meter that were known at the moment, now we know more of them. TU Dresden with the impedance meter developed and manufactured by Spitzenberger and Spies, the impedance meter for more energy, the one that has been developed for research activity, especially for communication in Bilbao at UPV, and the one that we have developed ourselves. So the 5 equipments include also, of course, a vector network analyzer for the characterization, an indigenized impedance. So the 4 devices are presented here. We have listed, I don't go through all the differences here, but you can see the difference, especially in the in-feed current to create the perturbation and to be able to measure something. We work, for instance, with a very low RMS current for the perturbation at single frequency, and we make steps. The same is a bit used for the IMD 300, but the current is much larger in that case, so a stronger amplifier. And UPV is also generating a perturbation, but this time in voltage, also very low energy, and also with then with a sweep over the whole frequency range. For the ONI 690, we have very different behavior. We use switch controllable load and with randomly pulsed signals, so we have a broadband excitation. So we can see that methods already for generating the disturbance are different, and the analysis of signals are also very different. In some case FFT, most of the case FFT or DFT, but we use similarly, as Professor Baumiller showed, some demodulation, dual phase demodulation or locking amplifier technology. Now the results, most exciting part. For the static impedance without energy, so we have very good coherence between tests. One device is a bit changing the resonance frequency and magnitude, probably to the connection. So we have to discuss a bit that. How do we connect the load and measure the load? For the energized comparison, this is always the static impedance. We are not so far with the programmable and time variant impedance. There we see this very strong impact on the supply of the grid. We have used, in some cases, a grid simulator, in some cases directly the net, and you can see that in low frequency this has a very strong influence. So we have to coordinate our tests and define the test condition more accurately regarding to this. But generally speaking, very satisfying correlation between the tests, up to 150 kilohertz at least. All right, it's time to draw a couple of conclusions. So we have been able to compare devices and for the static impedance successfully. Now the time varying and programmable impedance from METAS is available for further comparative tests. I guess every partners of the ZNet project will make some tests, maybe some other institution too. We have methods to model the grid slowly that are coming, and this gives us tools and methods how to investigate and tackle better the impact on power line communication and maybe other issues, for instance, converter stabilities. We need to work better on this impact of subcycle time varying grid impedance. There are so many scenarios. It's not clear how and which one will really impact on the PLC in which conditions. So it would be very interesting to develop this further. In that sense, this time varying sample can be very useful. But the time and the work, the resources to go to a standardized measuring method is still very long due to the different methods and the first steps that where we are. So thank you for your attention. I hope this was giving some good insights on the standardization process that is started with this ZNet project. And I'm pleased to hear your questions if there are. Otherwise, you write to us your questions. We have here the contact information. Thank you for your attention. Thank you for all the partners of the project and from the funder, of course, Swiss Federal Office and Energy as a main funder.